Thank you. So welcome to my presentation. As you said, I will be talking about greases and grease analysis, and my focus is going to be on optimizing grease replenishment intervals and seeing how we first get good data for that by taking good grease samples, and then using oxidation trending is what we'll find here. So let me advance to my first slide. And I'm going to talk a little bit about the progress of machinery greasing and how maybe we started adding greases to machines and how it's evolved over time. And I think if some point in time you go back, you hear historically, pump until you see it come out somewhere, or we hear phrases like the squeaky wheel gets the grease. And we use it in different ways, but it probably had some validity in how people determined when is it time to grease some machinery and how much do I add. And if those things are not correct for the application, it's not really optimized. And so we've got some improved approaches that we can use to enhance the greasing process. And that would include having lubrication rounds, having scheduled activities to go from machine to machine and address the lubrication. Maybe these rounds or the guidance here includes the number of pumps. You know, I've heard over the years, I've spoken to folks who are on the front lines and maintaining assets, and I, from time to time hear things like, well, 3 shots of grease should do the trick. And sometimes it's just believed that any grease would get the job done. But we can move from there to more precision greasing, and that's where we have calibrated grease guns and even clear grease guns that let us confirm and ensure that it's the right product for the application. We see color-coded products, color-coded fittings, so we know which grease goes where on a machine train. Grease meters that help us put quantities out there, barcodes that make sure we're on the right component, and electronic rounds to drive that process. And then we can even move up from that precision greasing into conditioned-based greasing, and really a method that's out there now and it's getting a more widespread use, and it's really great, is using an ultrasonic transducer to get feedback to the process. So that helps us identify, is there a need to grease here? Are we inadequately lubricated and we need to add grease to get back to a condition of a full separation, a fluid film, an elasto-hydrodynamic film in that application? And can we use that feedback to know when we are at risk of overgreasing, because we can hear the churning of the excess grease. And so it gives us that feedback to the process. It allows us to go from, pump until the grease comes out somewhere to now having some kind of feedback mechanism. And I'm going to say that the next step along the way would be to incorporate equipment sampling and analysis to optimize that lubricant life and its performance over that life. So the starting point here is to realize that grease is different. It's not the same as oil. Viscosity, which we speak about, is the property of an oil that sets the lubricating film and dictates how oil is going to flow. Grease is an oil. It's a base oil and some additives to which we've added a thickener, and it's designed to stay in place in the machine. We can describe grease behavior as non-Newtonian, meaning that its viscous behavior is shear dependent. Newtonian fluids, the viscosity is going to be independent of that shear rate, but grease definitely is. And we can see grease behavior change as we change the shear rate. And the rate at which the grease starts to behave in a more fluid manner rather than a solid or semi-solid, that varies with temperature as well. So dynamically, within a machine, we may have a situation that allows grease to flow, but maybe only very close to the bearing or gear or whatever's moving inside that machine. And if we get further away from that close location, we are now in a zone of the machine where grease really isn't moving. It's not being, let's say, updated with the current status of the grease itself that's doing the lubricating, or of any contaminants that are present, or any wear particles that are being generated. So the sampling and analysis techniques that work well for oil are typically inadequate for grease. Oil being a Newtonian fluid, if we can introduce a tube or a syringe and break the surface of the oil and then pull a vacuum, we can transfer, we can induce flow in the body of oil to get that into a sample container. But that may not be enough to get grease to flow unless it happens to be a very soft fluid grease. And the problem is that often we're just trying to get that sample and some grease comes out. But if it's not the grease that's close to the component, it's not going to tell us the story. So I'm going to introduce this grease thief tool, and it's kind of like a blood test for machinery. It comes out of ASTM D7718, which is a standard that was developed originally in 2009 and through the work of volunteers at ASTM was published in 2011. The background for setting what the standards should be for obtaining a representative grease sample started in some industry research that took place. Some folks in the Danish wind industry, including Vattenfall, Dong Energy, and some others like Covey, participated in that and developed new approaches to getting grease samples from both main bearings and blade bearings in wind turbines. And the Electric Power Research Institute has been involved in a number of research projects that evaluated and developed some approaches for sampling grease from gear components and validated the results. So we've got some inclusion in this standard of some historical methods for sampling, like trying to use a syringe or maybe using a tongue depressor or a popsicle stick or something like that to kind of dig grease out. And certainly you can get a grease sample, but this method gives some cautions about that and some care that needs to be used in obtaining that sample or maybe multiple samples. So the use of tubing and the adequacy of suction alone, along with the possibility of actually ending up with some peripheral grease, some grease that's not really doing the work of lubrication, is one of the big risks. So this method did include some new technologies for active and passive sampling. And these are the grease thief samplers. You can see one of them here at the far left. That's a photograph of it. Consists of a clear plastic body. You see the red plastic piston that fits within, has a precision fit to the inside bore of that plastic body, and then a white handle that allows that piston to be moved back and forth. But unlike a syringe that might have similar components, and we pull back on the handle to create a vacuum and get the grease to flow, generally these thief samplers are being used in a coring type process. And you can see one installed in a T-handle at the bottom. And that T-handle device allows you to keep the piston over the end of the grease thief or the container, so that as you enter into say a reservoir or a bearing housing or a gearbox, it's pushing grease out of the way. That peripheral grease that may not tell the story kind of gets moved out of the way until we get close enough that we can then advance just the body portion. The piston stays in place, the body goes forward, and it's a coring action. The piston fitting inside that body creates a seal, and that allows us, when we withdraw this thief sampler, it's going to bring the grease with it, as opposed to a piece of tubing, which if we run the tubing in and pull it out, a good bit of that grease may, through the cohesive forces in the grease, be tugged right back out of that tubing again. And what we end up with is the grease that's buried in that tube that came from just inside of our access plug, perhaps. So these are the tools that are available. You see drawings here are two different styles. One is considered a passive one that just has the piston and the handle. The one on the right also has this stinger probe. And the stinger probe helps us in those applications when we don't know exactly how far into the machine is the target that we want to sample, the face of the gear or the bearing. And so we can insert it until we feel that stinger probe touch the surface, and then core that sample by advancing the body. And so different kits have been developed that allow, have different makeup, different tools, perhaps different instructions that put together these thief samplers along with some instructions, some labels, perhaps secondary tools that come in handy, like a spatula, maybe a syringe to transfer the grease into the grease thief. And really, these kits can cover most of the grease sampling challenges that are out there. So I'll talk about a few examples and talk about how sampling these locations can help us in optimization. So one of these is going to be the robot sampling. So we've got a 6-axis robot here that we might see in automotive or other manufacturing settings. These robots can be quite large and have significant payloads. At other times, they might be doing very lightly loaded redundant tasks or repetitive tasks, like maybe spot welding or painting, delivering a stream of paint to components. So there's a lot of variation in how they're loaded, how they're worked, what kind of environment they're in, what kind of contaminants are there. But historically, greasing these robots would consist of a calendar basis, a time-based activity to purge all of the old grease out and put new grease in. So we've done some work with some grease operators, I'm sorry, some robot asset owners, and worked with them to take a series of samples from robots with vastly different loading, different cycles, different kind of environments, different temperatures. And we compared the results of greases taken using one of these kits. And what we found was, and it wasn't always intuitive, sometimes we found grease that was significantly oxidized or perhaps significantly subjected to shear stress, so that the consistency of the grease was changing. And sometimes it was on a heavier loaded. A lot of times it was on a short movement that happened frequently. So there's this variability, but this allows us, once we have the grease analysis results, to transition from this historical time-based grease purge to a condition-based approach. And one of the customers we worked with, they had already documented significant savings of nearly $1,000 per year on each of these robots in saved grease consumption costs. Now, there was a trade-off. Some of the components needed to be greased more often, and others we were able to extend out that interval, but it was optimized based off of the condition of the grease and the variables that are out there that influence what that true life of the grease is. So we're going from time-based or feedback-based to really understanding what's the condition of the grease. And we look at a couple of different factors. We've done the same thing in wind turbines as well. You know, the sampling, getting the sampling is real critical here. The grease flow is dependent on the temperature and bearing movement. We use, here you can see that grease thief loaded into a handle again, and it allows us to get into that location. There's a photograph here of an early iteration of a handle that was, you know, we used the information from that study to come up with an improved design that allowed us to get a consistent sample right from the face of those rollers each and every time. And this project was really helpful because not only could we take that sample and analyze it, that was already scheduled. Some of these bearings were already scheduled to be taken down and overhauled. So there was the opportunity to tear them apart, to look inside and see what the real condition of the grease and the bearing was. And in each case, it matched up to what we were seeing in the grease samples. Sometimes folks say, well, you can't count on a grease sample unless you dig it out from underneath the rollers, and it becomes this very intrusive process. And in this case anyway, we're able to show that a grease sample that was cored using the ASTM method, ASTM D7718, and was cored from the face of the roller, gave us the same results as the grease sample that was later dug out from under those rollers, because the rollers drag the grease around to create this fluid-like flow, and you get a representative population of grease right at the face of that component. Sometimes we need to be accessing equipment with even smaller openings, and so there's some tools to do that. This particular tool was designed to take samples from openings as small as 8 millimeters in diameter and be able to transfer them out. But the principle here is the same. You still have a piston that fits within a tube with a precision fit, and that allows us to core that sample. Pillar block bearings, another application. Sometimes these can be very critical. One of the first applications that we used, or challenges that we used as the motivation to develop these samplers, was in the National Institutes of Health, looking at air handler unit fans. We were able to identify grease mixing in some cases, the presence of contaminants along with wear levels, and maybe as a complement to say vibration analysis or mechanical ultrasound condition determination, we were able to get down to the root causes. And sometimes these root causes had to do with the wrong grease being present, or in the case of this bearing shown in this picture, 2 different greases being mixed in that reservoir or in that housing, pillar block housing, one being a lithium complex, the other being an incompatible polyurea, and the result being loss of the oil film, metal to metal contact, and damage of the bearing. So there's some discussions here about the analysis process, and you can see we've got a ferrous debris checker here. There's the dye extrusion process, which allows us to measure the consistency of the grease, colorimetry, where we can compare that to the color of the new grease, linear sweep voltammetry. Again, the folks bringing this symposium together bring us that technology, the ruler technology, which can be applied to greases, and very effectively with this approach where we have the grease thief analyzer creates this thin film on a substrate that you see at the top, that long photograph with the barcode. That's actually a layer of grease. It happens to be new grease, and it's in various sections that can be peeled away. One of them can go right into a ruler vial to give us a consistent thin film for measuring the presence of the antioxidants. And that really goes to some of the examples that I've added in here. Here's some of the report data that we're getting out of the analysis, but we're really able to do 10 different tests, including looking at some of the metals through metal spectroscopy. We're using RDE there, again, using the ruler technology for antioxidant levels, measuring the consistency of the grease. And that the consistency is important as well when determining how often do I need to relubricate, because the consistency changes and then the grease may not stay where it's supposed to. It may create a wall, what we call tunneling or channeling, or it may get so soft that it runs out or separates and it fails to lubricate that component. So looking at all these different properties of the grease as well as the presence of contaminants helps us understand, is this grease suitable for continued service? Also, with the contamination piece is the cleanliness, and we're able to create a visual representation of the particulate. And that's what this representation is here. And I don't know if you guys will see this in real time, but there's a quick video here that looks at a couple of substrate examples. First ones are pretty clean, but now you see the appearance of the particulate suspended in the grease. And it helps us understand what's going on with a used grease, but this can even be applied to new greases to make sure that the new greases we're putting into our critical machinery start out clean, stay clean, and give our machine maximum life. But if a grease like this is what's going into your machine from your grease gun or your auto luber, it's going to start fatigue wear and abrasive wear right off the bat. Other contaminants that are measured include moisture analysis, where one of the real good methods that we have available now, part of this ASTM D7918 standard for in-service grease analysis, uses a heated dry air transfer to a humidity sensor and gives us parts per million levels of moisture in grease. So if we can figure out, the cleanliness of new greases and make sure that our grease supply is kept clean, is procured clean, is kept clean, right up to the point where it gets into the machine, we can see extended machine life and a great return on investment. So I want to give a couple of case studies here. The first one I kind of mentioned in the study that we did with the automotive manufacturer. I talked about the nearly $1,000 per year saving per robot. And, this is how this was done, taking the samples from these robot gears, 6 different locations on the robot, and overall a significant reduction in the cost of operating that asset without even taking into account that we now have data about possible damage or the reliability of that component. And that becomes very important as well in scheduling outages and downtime, or just knowing in advance that a robot needs some maintenance attention, that there may be a degraded component wearing inside. Another case here from the wind turbine. This is a blade bearing example using the Grease Thief Slim in that photograph to take that sample. And the method was developed a couple different ways on some ground level failed blade bearings that were accessible, where we could see where can you go, what's going to get you close to the component, what sample is going to be representative, and some shop sampling there. By the way, there's for wind turbine asset owners, there is a couple standards out there. AWEA, the American Wind Energy Association, has a number of standards that address sampling greases from blade, main, and generator bearings, and also a standard with guidance on the analysis to do. So the results that we found really clearly correlated to the as-found condition of the wear and of the grease. My final example is from a military helicopter example. We put together a specific kit for that environment that allowed these soldiers to be able to take samples during their scheduled maintenance and evaluate how an existing time-based grease program was working. And we developed this oxidation rating, which looked at both of some of the greases had 2 antioxidants, some only had 1. We created an index that weighted them so that they could be compared. And you can see this example in one of the locations, a drive collar location, that as you plot out the oxidation index as a function of equipment hours, it becomes clear that we're losing a significant amount of antioxidants. And really the residual point here would be an index number of 50 that would correspond to typically what we shoot for or I should say 75. And at that point where this line crosses that graph, we're only talking about 175 hours. That was actually less than the existing guidance for PMs or periodic change out. So in this case, we were able to get a 43% reduction in lubrication tasks per 1,000 flight hours, and the service interruptions, how often these helicopters had to come back for maintenance, that was cut in half. So significant improvements, significant cost benefit. So how do I get this started? Well, find your critical applications, high-risk components for analysis, review your sampling kit options, look at the accessibility that you have. How can I get to the grease? When is it accessible? Some machines are only accessible at certain times or certain operating conditions. And one thing about grease that's different than oil, with oil, we always say, get to the machine while it's running and take the sample, or sample it just after it shuts down, while all of the particulate, especially the wear particles, are in suspension, and we get them in the sample. Well, when we shut down a grease lubricated equipment, piece of machinery, there's no settling. So that same sense of urgency is not there to rush right in and get the sample, or even to get the sample while the machine is running. So from a safety perspective, it may be a little bit better that we can shut down a machine and then take our time, find the right location, and then use the tools that are there in the ASTM D7718 standard and use that to access the live zone location. So I had some of the analysis tests here and some of the further tests that can be done. But I just want to turn it over now and see if there's any time for any questions.